Hey, welcome to my YouTube channel. I am Thalitakum Hutajulu from Udayana University Mechanical Engineering student. The purpose of this video was made to fulfill a linear algebra course assessment, also to educate about linear algebra. So this is my reference. So my reference from this book, Linear Algebra, Kuldeep Singh, step by step. Okay, so now we're going to learn general vector space in chapter 3, general vector space. Okay, the content from the general vector space is 3.1, introduction to general vector space, 3.2, space of vector space, 3.3, linear independence and basic. Okay. 3.1 Introduction to General Vector Space. 3.1.1 Vector Space. In the last chapter, we have already learned about vector space, right? Okay, the set V is called a vector space if it satisfies the following 10 expressions. So we say that if the element of the set V satisfy about 10 x1, then V is called a vector space and the elements are known as a vector. So this is 10 x1s. 1. The vector addition U plus V is also in the vector space V. 2. Commutative law. 3. Associative law. And 4. Natural elements. Additive force. 6. Let K be a real scalar, then K is also in V. 7. Associative law for scalar multiplication. 8. Distributive law for vector. 9. Distributive law for scalar, and finally identity element for every vector U in V. Okay, 3.1.2 example for vector space. We have PT, KT, and RT. So adding two vectors or two polynomials. This is our formula. We get the PT plus KT. So the hence from PT plus KT is in PT, which means that we have closure under addition. And to commutative law, we are required to show that PT plus KT equal KT plus PT. So this is implies kebalikan dari PT P times T plus Q times T. Okay, then the hence from that is Q times T plus P times T. Okay, this is application to in coordinate cartesius. So this is fx, ax. This is A and B. So the vector addition, the sum f plus g is also in FAB, and f plus g times x equal f times x plus g times x. Scalar multiplication, let K be a real scalar, then for all x in A and B. So kf times x equal kf times x. Basic properties of general vector space 3.1.3. So this is a basic properties of general vector space. A k o equals 0, o equals 0, and min 1 times o equal min o, min u, o, and d if ko equal 0 or o, then k equal 0 or o equal o. So this is a proof. Proof from A. Need to prove ko equal o by applying the above examples or examples from the 10 examples. So this is example number 4. U plus O equal O. We have applying examples number 5, which is that k times u plus v equal k times u plus k times v. So this is hence ko plus ko. So adding min ko to both sides of this ko equal ko plus ko give O equal ko. So this is we get from the example number 5, u plus min u equal O. So hence we have our required result ko equal O. So B, proof from B required to prove O equal O for real number 0 equals 0 plus 0. We have O equal O plus O equal times O. So equal O times O plus O times O. So we get from examples number 9. And k plus c times u equal ko plus co. So and then we have result B, that is O equal O. So this is our proof. See, and we get from the required to prove min 1 u equal min u, adding u to min 1 times u give 1 min 1 times u equal 0 times u O by part B. This by part B in here. So we get u plus min u equal O. So u plus min u times O equal O. So we get u times min 1 u plus min 1 times O equal u plus min u. So we get finally we get min 1 times u equal min u. So this is a proof from the need to prove that KO equal O. If plus K equal 0 or U equal O. U equal O. If K not equal 0 or non-zero, then KU equal U. So, and the last we have 1U equal O. So since 1U equal O, therefore U equal O, which is our vector result. If K equal 0, then clearly the result holds, because 0 or O0 equal O by part B. So we back to the part B. And next, in 3.2, surface of a vector space. This is a set S or surface. This is a surface, or we can call the subset S a non-empty subset S. Vector space. Vector space V is called a surface of V. So this is a surface of V. It also a vector space with respect to the same vector addition and scalar multiplication as V, right? So subset S there is in a vector space V. So if the S in a V, we can call that is a surface of V. So 3.2.1 example of vector surface. A subset is merely a specific set of element comes from V. So this is element from V. This is element from V. A subset must also satisfy the 10 extremes of vector space to be called a surface. So if a subset S not satisfy to the 10 extremes, so this is not surface, right? But if a subset satisfy the 10 extremes, so we can call that is a surface of V. Okay, this is a set S. The set S with the single element O is a surface of R quadrat or R2. This is an application in the coordinate Cartesius. So this is R2. P equal R quadrat. So S is a surface of V. So S, this is S in here is the surface of V. So let S be a non-empty subset of a vector space V. Then S is surface of V. A. If U and V are vector in the set S, then the vector addition U plus V is also in S. So like that, this is a vector addition. So U plus V in S and also in V. So and B, if U is a vector in S, then for every scalar K, we have Ku is also in S. So if if u is a vector S, so this is a vector in S. Then for every scalar k in S also. So k times O is also in S. So this is a scalar multiplication. Example A, if U and V are vector in the set S, then the vector addition U plus V is also in S. And B, if U is a vector in S and K is any real scalar, then KU is also in S. We have U and V be vector in S, then U plus V, we have a formula U and V, U plus V, so U and plus, so equal 0 and A plus B. So which is in the set S, and K times U equal 0 and K times A. So closure under scalar multiplication, that this is a closure under vector addition. So this is a application in the coordinate Cartesius. The set S is a surface in our quadrant. Okay. Example more. Let S be the subset of vector in the form X and Y. And Y. So we have K equal number 1, mean 1, U equal 1 and 2, so K times O is equal mean 1, mean 2. So this is not a subset. This is not a surface of our quadrant, because the hands from the subset is not we have to know that I mean because this shaded region S is not a surface of our quadrant, because X not equal O or atau tidak sama dengan 0 atau lebih atau sama dengan 0. Jadi kalau kurang dari 0 dia bukan subset, bukan surface. Okay, because the first entry in the vector is mean 1. So the first entry in the vector is mean 1, which is this, that 0, and the set S only contains vector of the from X, Y, where the first entry greater than or equal to 0, right? Greater than or equal to 0. Greater than or equal to 0. A revision of linear combination. Linear combination combines the two fundamental operation of linear algebra, vector addition and scalar multiplication. The definition of linear combination is the vectors that v1, v2, and until vn be vector in a vector space. If a vector x can be expressed as, this is a formula, and we can express like this, then we say x is a linear combination of a vector of the vector v1, v2, v3 until vn. Okay, example, ku plus cv is in S for any vector u in v in S. We have u a b 0 transpose and v b in S. Then for real scalar k1 and k2 we have, this is a formula, right? So u we can transpose, and v we transpose too. So we get the k1 times u plus k2 times v is also in v. So as in surface of v, any linear combination, so this is a linear combination, ku plus cv is also in S. So ku and cv is also in S. So this is a application in 3D. In 3D. 3 dimension surface in 3D, right? Surface of R3. So x, y, 0 as the set as x, y, 0 and 0 equal, and z equal 0. So S contains the set of vector in R3 such that the last entry in 0. Revision of spanning set that if every vector in V can be produced by a linear combination of vector V1, V2, V3, and Vn, then the vector span or generate the vector space V. So example, U and span the line Y equal X in R2. Any vector in this line is element of span U. This is a span U and this is a U. This is an application in the coordinate Cartesius. So span U, surface, right? Surface. So span S equals subspace because span S in V. Example, we have A, B, and C. So matrix T 1, 2, min 4, min 2. Okay, the span A, B, and C. This is a formula. So we application the formula to the A, B, and C. We get a K equal 1. So K in here we substitute to the equation 3. this is equation 1, 2, and 3. So we substituting to the equation 3. So if the K3 equal mean 1, so and K1 mean equal 1 and K3 equal mean 3, we substitute it to the last equation. This is a last equation, and give K2 equal 2. So hence we have found scalar K1 equal 1, K2 equal 2, and K3 equal mean 1, which satisfy, this is satisfy A plus 2B mean C equal D. Therefore, D belongs to span B, A, B, C, because D can be made by a linear combination of A, B, and C. So A, B, and C, a linear combination. Summary from the what we can get from the learn today. Summary is the set S is the surface, is a surface of a vector space if A, S is less under vector addition, B, S is less under scalar multiplication if a vector X can be expressed as the formula. Okay, we next in here 3.3 linear independence and basic. So 3.3.1 linear independence. So in the previous chapter we have already learned about linear dependence, right? Vector v1, v2, v3 until vn in v are linearly dependent. The only real scalar k1, k2, k3 and until kn which satisfy the formula Q1 times V1 plus Q2 times V2 plus Q3 times V3 until Kn times Vn equal O or 0 are Q1 equal Q2 equal Q3 until Kn equals 0. Example A and B, we have A and B. So that the matrix A and B are linearly dependent, we have a formula Ka plus Cb equal O. So this is a matrix O. So we apply the formula for the problems in here. So we get a K equal O equal 0 and 2C equal 0. So K equals 0 and C equals 0. Conclusion that the given matrix A and B are linear independent, right? Because the hence from the A and B is a 0. Okay, 3.3.2 linear dependence. Okay, linear dependence. The vector v1, v2, v3 and v until vn in the vector space V are linearly dependent. The scalar q1, q2, q3 until kn are not all 0 and satisfy. So not all the hands or the answer from the linear dependence not all a 0. So maybe min 1, min 2, or 2 or 3, not all 0, right? And satisfy. This is a formula for the linear dependence. So this is an example. We have u, v, and y. Y equal to b factor in v. So that the factor u, v, and y are linearly dependent. So cos quadrat x plus sin quadrat x equal 1. So we multiplying each side by 2 gives 2 times u plus 2 times v equal y. Because u is a cos, because u times cos quadrat x, v, and y equal to, so this is hence or get from the formula, we get from the formula 2 times u plus 2 times v. Well, v implies that we can make vector y out of a linear combination of vector u and v. So 2 lots of u plus 2 lots of v. Therefore, vector u, v, and y are linear dependent. So this is a linear dependence. Okay, 3.3.3 properties of linear dependence and independence. So two vector u and v in a vector space V are linearly dependent. One of the vector is multiple of the other. Assumes vector u and v are linear dependent. There must be not zero scalar k or c such that k, this is a formula, k o plus cv equal o. So first k equal 0, then ko equal min cv. So this is u, and the formula we have u equal mv, and m is a scalar. Therefore, the vector u is multiple of the vector v, right? And the last we get a u mean mv equal o or 0. Vector u and v are linear dependent, so this is a linear dependent. So a vector u and v in the problem is a linear dependent. Example: we have a vector so that the set of vectors subvector are linearly dependent. So not the node of polynomials can be written as a linear combination of the preceding polynomials. For example, we can write the polynomials such as tk as a linear combination of bases with scalar. So this is our formula. The formula is not equal. The since node of the polynomial is a linear combination of the preceding polynomials, we conclude that the given set is the linear dependent. So this is a 3.3.4 basic vector. So we have two basic vector. Consider the n vector v1, v2, v3 until vn in the vector space V. This vector for a basic of V. So 1, v1 until vn span V. v1 until vn are linearly dependent. So n vector v1 until vn as a set like that, B equal v1 until vn. So these are generally called the basic vector. This is a basic vector. For example, we have vector S. So it's a basic for Pn. 1. The set of vector S must span Pn. So span, this is a span. So from this span we have a vector, and this is a vector S. So we get in the vector to the formula. So hence from the vector is hence the vectors 1 until Tn is a span of Pn. So vector S is a basic for Pn. And 2, the set of vector S must be linearly independent. So this is a linearly dependence because not equal to Tk. Since no polynomials are linear combination of the previous polynomial, the conclusion is that given set or vector S linearly dependent. So this is a linearly dependent. So example, illustrate that this function repeats every 2v interval. So this is a formula if we use intervals. This is application in the coordinate Cartesius or the coordinate interval. This periodic function Y is made up of linear combination of sin x, sin 3x, sin 5x, any function in the vector space of F, O, and 2v of the form. So this is a formula. So the formula So the formula we will use in the problems. So if the problems use the sin or cos, so we use the formula. Okay, uniqueness. So this is a uniqueness. Using a basic for a vector space is essentially choosing a coordinate system which allow its vector to be expressed equivalently. So proposition that the set B V1 until Vn be a basic basis for a vector space V. So proof we have a since B, we have a set B. So this is there exist set scalar Q1 until Kn such that formula. Suppose we can read the vector y as another linear combination. It's a linear combination. Q1 equals C1, Q2 equals C2 until Kn equals Cn. So, and we get the Kn until Kn equals Cn finally. So this is Q1 means C1 equal 0, Q2 means C2 equal 0, and hence that we get from the formula is Kn equals Cn. So hence have proved that the basis vector, the representation of any vector is unique. So why is unique? Because K1 equal C1, so K1 means C1 equals 0. So all the answer from the formula is 0 or the same with K1 equals C1, K2 equals C2, K3 equals C3, and last we get the Kn equals Cn. Okay, the summary, consider the linear combination. This is a formula of the only solution. The only solution is K1 until Kn equal 0. So then the vector V1 until Kn are linearly dependent. Otherwise, they are dependent. Definition. Vector B. This is a vector B of the vector space V from a basis of V. So 1 span V and 2 are linearly dependent. Okay, this might explain. And finally, thank you for watching.